In the last video, we mentioned constitutional isomers, as well as cis-trans isometry. One of the central concepts of cis-trans isometry is that double bonds cannot rotate around one another. However, single bonds can. In chemical terms, we like to say that single carbon-carbon bonds exhibit free rotation. Similar to cis-trans isometry, the groups bonded to single bonded carbons can be compared to another in 3D space. But how do we do that? How do we visualize that two groups connected by single bonded carbons are located in a particular location in 3D space? Enter Newman projections. Just like the bond line structures you're familiar with now, Newman projections are another way to visualize organic molecules. I want you to understand that when we draw bond line structures, we're visualizing them in the plane of a paper. If you're watching this video on a screen and you have a notebook in front of you, look at your notebook from above. The bond line structure we've been drawing this whole time would be flat on your notebook, like so. To draw Newman projections, we need to change our perspective of bond line formulas. Instead of looking at these molecules from above, we move our perspective to looking across a bond. It helps to literally move your head like I do. This way we end up with a front carbon as well as a back carbon. There's three substituents on each front and back carbons are the substituents we end up comparing in Newman projections. To figure out how to draw Newman projections, let's use an example of 2,3-dibromo, 2,3-dimethylpentane. Take a moment to draw out the molecule as a bond line structure. Hopefully your molecule looks like this. To practice drawing a Newman projection, let's say I want to visualize this molecule looking down the C2-C3 bond, or turn my head to the left to look across the second and third carbons. To draw the front carbon, or C2, we draw a filled-in circle. To draw the substituents connected to the second carbon, draw three lines to make a Y, or a peace sign. I suggest doing a Y on the front carbon, since on our bond line, two substituents seem to face up, while one substituent faces down. The back carbon would be shown as a wide circle around the front carbon. To draw the substituents connected to the third carbon, draw either a Y or a peace sign, but make sure it doesn't overlay your front carbon. Fill in your substituents on each of the carbons. There's some really good information Newman projections can give us. First of all, on each carbon, the three substituents are as far away from each other as possible. However, notice that on each front and back carbon, we didn't have any information on whether the substituents are on wedges or dashes. Therefore, it doesn't matter on which line you put the substituents. The whole point is once again free rotation. These substituents can rotate above the carbon to orientate themselves in different ways. But what if I specify 3D location on the bond line structure, like in the example below? On carbon 2, bromine is on a wedge, while chlorine is on a dash. Remember that wedges mean that bromine sticks out of the plane of the paper, while the dash means that the methyl sticks behind of the plane of the paper. I always liked sticking my pencil on top of the paper to signify the wedge, and under my paper to signify the dash. If we now try to draw the Newman projection from C2 to C3, we will end up once again twisting our head to look down the bond. Once we twist our head, the bromine, or the pencil sticking up, is on our right side, while the chlorine, or the pencil sticking down, is on our left side. On the Newman projection then, the bromine must be on the right, and the chlorine must be on the left. The remaining substituent, the methyl, on the line, just points down. We can figure out carbon 3 the same way. On carbon 3, bromine is again on a wedge, while chlorine is again on a dash. Twist your head to look down the C2-C3 bond, and bromine will appear on your right, while chlorine will appear on your left. Therefore, we draw the back carbon with bromine on the right and chlorine on the left, and a remaining methyl on a line as up. Unlike the previous example, we need to draw the substituents in this way. The reason is because the bond line structures specify the 3D orientation of the substituents. It would be incorrect to draw the Newman projection in any other way. Let's try drawing the same structure, but this time from C3 to C2. This time you have to twist your head the other way to look across the bond from the other side. This time the bromine on C3 ends up on your left and the chlorine appears on the right. The remaining methyl substituent faces up. On C2, bromine ends up on the left and chlorine appears on the right. The remaining methyl substituent ends up facing down. Notice that when we change the direction from which we look down the bond, the direction of the substituents changes. I like teaching to repeat this trick with a pencil sticking up or down, and literally twisting your head to look down the bond on the structure. You end up not having to memorize anything, and you'll never make a mistake on a Newman projection. Now that we know what Newman projections are and how to draw them, I want to spend some time analyzing Newman projections and determining some of their properties. First, take a second to try drawing the Newman projection for the C2-C3 bond for butane. The Newman projection should look something like this, with 2 hydrogens and 1 methyl connected to both the front and back carbons. However, you may have the substituents oriented in different ways. You wouldn't be incorrect if they were. The reason for that is because I did not specify the type of conformation to draw. Notice that in my drawing, the methyl substituents are the largest group on both the front and back carbons. Also notice that the methyl are both as far apart from each other as possible, and the bonds on the front and back carbons don't overlap. This conformation is called the anti-staggered. The anti refers to the fact that the largest groups are as far apart as possible, and the staggered refers to the fact that none of the bonds overlap. Since there is the most possible amount of space between the atoms, this would be the most stable conformation possible. The anti-staggered conformation will be the conformation with the least amount of potential energy. Let's rotate the front carbon. This time, the largest groups are not as far apart as possible, but the bonds on each the front and back carbon still don't overlap. This conformation is called the gauche conformation. The bulky substituents on the Newman projection are not as far away from each other as possible, but the conformation still isn't entirely unstable. The gauche conformation has significantly more energy than the anti-staggered conformations, but doesn't have the most potential energy possible. The last conformation involves overlapping the groups on the front and back carbons. When the substituents on the front and back carbons are overlapped, there exists a significant amount of repulsive force, and the molecule is therefore relatively unstable. However, the most unstable conformation involves specifically overlapping the larger substituents, in this case, methyl. All these conformations are called eclipsed, and will be the least stable and highest in energy of the possible conformations. Therefore, when drawing Newman projections that doesn't specify 3D locations or wedges and dashes, check the question to see if you're tasked with drawing the most stable or least stable conformation, or in other words, the conformation with most energy or least energy. This concludes our discussion of conformers and covers yet another form of isometry that can exist in organic chemistry. In the next video, we'll move on to discussing the conformation of cyclohexane, a concept somewhat related to what we just covered. Practice Newman projections with the worksheets and answer keys linked in the description below. See you guys in the next video.